Physics Part 179. Young's double-slit experiment. Condition for constructive interference path difference, nano lambda. Condition for destructive interference path difference, n plus 1 over 2 into lambda. Fringe width x is equal to lambda d over a, where a is the separation of the source slits and the d is the distance of the screen from the slits. Section questions. Number 1. Compare two source experiments to demonstrate the interference of sound waves with a Young's double-slit experiment using light. What are the similarities and differences between the two experiments? 2a. Explain the term coherence as applied to waves from two sources. 2b. Describe how you would produce two coherent sources of light. 2c. A double-slit interference pattern is produced using the slits separated by 0.45 millimeter, illuminated with the light of wavelength 633 nanometer from a laser. The pattern is projected onto a wall 2.50 meter from these slits. Calculate the fringe separation. Number 3. The figure shows the arrangement for obtaining interference fringes in a Young's double-slit experiment. Describe and explain what will be seen on the screen if the arrangement is altered in each of the following ways. A. The slit separation is halved. The slit separation A is halved. B. The distance d from slits to screen is doubled. C. The monochromatic light source is replaced with a white light source. D. A piece of Polaroid is placed in front of each slit. The polarizing directions of the Polaroids being vertical for one slit and horizontal to the other. Stationary waves. Well, at the end of this section, you should be able to know more about stationary waves. You should be able to show an understanding of the experiments which demonstrate the formation of stationary waves using microwaves, stretched strings, and air columns. Explain the formation of a stationary wave using a graphical method and identify modes and antinodes. Determine the wavelength of the sound using stationary waves. The notes we hear from cello are created by the vibrations of its strings. The waves patterns on the vibrating strings are called stationary waves or standing waves. The waves in the air which carry sound to our ears transfer energy and so are called the progressive waves. The figure shows a single transverse pulse traveling along a slinky spring. The pulse is reflected when it reaches the fixed end. If a second pulse is sent along the slinky, the reflected pulse will pass through the outward going pulse, creating a new pulse shape. Interference will take place between the outward and reflected pulses. If the interval between the outward pulse is reduced and the progressive wave is generated, when the wave reaches the fixed end, it is reflected. We now have two progressive waves of equal frequency and amplitude and amplitude traveling in opposite directions on the same spring.